robust decision making. Thank you again, Jamie, for joining us today, and the floor is yours. Thanks.
Great, thank you. Excuse me, can you see my slides?
Yes,
Okay.
thank you.
Excellent. Thanks. Well, thank you very much for having me. Thank you to Yaga for the invitation and for everybody signing in. I saw a couple of names that I recognize, so it's great to see you again. So as Fa said, my research is primarily in data analytics and applications of machine learning and artificial intelligence, and even just traditional kind of regression analysis to look at monitoring equipment and processes, detecting when things start to deviate from our expectations, and then trying to diagnose the cause of that deviation, and then estimate how much longer we can operate before we need to take action. And so it's really focused on how we can take the data that we're already collecting in nuclear facilities and use those data to make better decisions to ideally save money and maintain our safety standards. And so I'll talk about that a little bit. But first I want to just introduce the department at the University of Tennessee in Knoxville in case people aren't familiar with it. So the Nuclear Engineering Department at UT was founded in 1957, which makes us the first nuclear engineering department in the country, although not necessarily the first program. And we have maintained a long, the long history of our department, in part through our close partnerships with Oak Ridge National Lab, with the Y-12 security complex, and with other local nuclear related companies. And so if we look within about 50 miles of where the campus is and where we're sitting in Knoxville, we have over 100 nuclear related companies that range from utilities and nuclear plant support service providers to medical applications, development of new radiopharmaceuticals and new imaging techniques, as well as application of radiopharmaceuticals and imaging techniques at Provision Proton Therapy at Thompson Cancer Center, and then of course all the way up to Oak Ridge and all of the R&D industry that has sprung up to support the missions at Oak Ridge and at Y-12 security complex. So we have a lot of activity here in Knoxville. I think it's an interesting area to be in if you're in the nuclear industry. So if you're into nuclear, I welcome you to come and visit Tennessee. And you can see here on the left our brand new building. This is the Xena Engineering Complex, which is nuclear engineering primarily on the side that's to the right of the picture, and our first year engineering programs on the left, and then you can see our football stadium right here. And so we have a brand new facility that we've been moving into over the last about 18 months. And so we've got new labs, new capabilities that we didn't have in our old space. If anyone was familiar with where we were prior to this building, I think you'd be super excited to see what we've got now. So just an open invitation to anybody. If you're ever in the East Tennessee area, please feel free to come by and visit the department. We'd be happy to show you around and have a discussion. So with that, the research that my group does really focuses on data analytics for situational awareness and for decision making. And so that encompasses a whole lot of stuff. And part of what I'll be talking about today is monitoring equipment and using that information for decision making, whether it's maintenance planning or operations and control planning. But we do a lot of work in how we can monitor equipment using the data that we're already collecting in our facilities without having to necessarily deploy brand new sensors, lots of new instrumentation. We also have spent a lot of time in our research group and in the industry in general, looking at how we can monitor the calibration of sensors while the plant is operating so that we can move away from time-based recalibration and calibration assessment of all of the sensors to condition-based calibration so that we can monitor the health of the sensors while the plant is operating and while the sensors are operating in their actual and operational conditions to see if there's any indication of decalibration of the sensors or other problems if the sensor is becoming particularly noisy, or if there's anything to indicate that we need to do maintenance on the sensor instead of just stopping and doing maintenance on all of the sensors at every outage. We've done a lot of work in kind of expanded concepts of operation. So a lot of that is looking at small modular reactors or advanced small modular reactors that can do things beyond just baseload electricity production. And so we've, and I'll talk a little bit about some of that later on in this presentation, but we've done a lot of work in that, and we have a new project, as Ify mentioned in the introduction, a new project really looking at how we can adapt our light water reactors and our current fleet of reactors to cogeneration systems and build out the technical basis for doing that so that we can improve the economic outlook for our current fleet of reactors and kind of keep them on the grid. I've done some work and we've done a variety of work in using the same data analytics techniques to monitor fuel reprocessing facilities. So I did some work with colleagues at Pacific Northwest National Lab and at Savannah River site to monitor the H Canyon facility. And I think I saw Nathan Gillum in the audience, so he did some work on this project too, where we were just looking at deploying commercial off-the-shelf kind of medium resolution gamma detectors and monitoring throughout the process to see if we could detect any indications of diversion, if we could understand what's happening, so monitor for process control, just to see what we can do with low-cost sensors and fairly straightforward data analytics techniques from a safeguards perspective, as well as from a process control perspective. And we've also looked at similar questions for pyroprocessing, for electrochemical reprocessing of fuel. We've done a lot of work in cybersecurity. And so again, the same data analytics techniques applied to a different type of data. So instead of only focusing on process data, we also incorporate in network data and packet capture data to try to understand if somebody has infiltrated the network, if they're trying to launch an attack or do something nefarious, or even just poke around and see what's going on in our system. Excuse me. And so, so kind of looking from a holistic view of not just the network and not just the facility, but combining those two sources of information together to see if we can detect any indication of an attack or of some sort of cyber event, whether that's an insider attack or an external attack. And finally, last thing that I'll quickly mention is that we've looked at using online monitoring and data analytics for monitoring additive manufacturing, so that when we build a part, we can eventually get to a point where we could qualify the part while it's being built, instead of having to build parts and do extensive qualification testing. I'm sorry, was there a question? So we're looking at, in this case, looked at some analysis of like low frequency IR videos. So again, nothing super expensive or challenging to collect the data, but looking at IR video of the build plate while a part is being built to detect any indication of voids or inclusions or just unexpected conditions in the manufacturing process. And so the hope is that eventually we can get to a point of being able to qualify parts that are manufactured through additive manufacturing for application in nuclear facilities. So we want to get away from expensive nuclear qualification processes. So like I said, today I'm going to talk a little bit more about the application specifically for equipment monitoring and process monitoring in nuclear power plants, and what we've done recently in that area. And so I'm sure everybody is aware that the Turkey Point reactor was the first U.S. reactor to get a license out to 80 years. I think this was approved at the end of 2019, and there have been a few other plants that have gotten their subsequent license renewal out to 80 years. There are, I think, 5 plants that have current applications that are under review at the NRC. So there's a lot of interest in continuing to operate the plants that that we've been operating, keeping our legacy plants on the grid, and which raises a lot of questions. We have things that are older than we expected them to be, and so how are we certain that they're going to operate the way that we expect them to operate? You know, if we think about, you know, you drive your car every day, you know, if you drive it every single day for 10 years, then you have some idea of what has worn out and what has failed in the past. So, you know, how often you need to change your oil, how often do you need to change your tires, how often you need to change your windshield wipers, things like that. But there may be new things that are going to degrade that just haven't worn out yet, that you haven't seen before. And so there's always a chance of emergent degradation that we just didn't expect. And so the current approach to deal with that is fairly conservative and fairly resource intensive, where we just add more inspection to say, like, well, we don't know what's going to happen with buried pipes over 60 to 80 years, so we're going to inspect them more frequently just to make sure that everything is okay. We don't know what's going to happen to the cables, so we will inspect them more frequently to ensure that everything is okay, which is good from the perspective of the assurance that you're not running into any unseen or unexpected degradation. But it's bad from the perspective of the economics of running the plant, because every time you add more inspections, you know, then that's more money, that's more labor, that's potentially more radiation exposure for your workers. And so we are interested in developing an alternative to just, we will inspect more and more and more to make sure that nothing happens that's unexpected. We also know that their reactors are shutting down. So there's some reactors and some utilities that are really committed to keeping their reactors online. And there are some utilities that operate in different types of markets that are unfortunately shutting their reactors down because they're just not economically competitive. And a big part of that, and really the most controllable part of that, is the operating expenses in terms of what we could reduce or manage. And one of the biggest contributors to these operating expenses is labor, right? And so there's the maintenance labor that is maybe overblown because we're doing additional maintenance inspection activities that we just don't need to do. And so we look at operations and maintenance as the largest addressable cost category in day-to-day operations of our current fleet of reactors, and really of our future fleet of reactors. And so anything that we can do to try to manage those costs helps improve the economic viability of the reactors so that we can keep reactors online and keep, you know, pushing electrons onto the grid. And so we kind of look at the current operations and maintenance paradigm in the US, at least the nuclear industry. We divide our assets or our components in our nuclear plants into active components and passive components. And the NRC has the maintenance rule that really defines the maintenance requirements and how maintenance is and inspection is planned and performed for active components. And it has aging management plans for passive components, especially as we go into license renewal and subsequent license renewal. But we see the operations and maintenance is somewhere from 60 to 70% of the cost of generating electricity, and a huge portion of that is labor. I will say this also includes security, which is a whole different issue, and there's a lot of really interesting work being done in automating security functions as well. That is not my research focus area, but that's another interesting application of automation and data analytics to try to drive down all these costs. But anyway, so our current approach is pretty much doing periodic inspection and maintenance. So every 6 months, every 18 months, every 36 months, whatever it is, we have a schedule by which we go and look at different classes of components and do an inspection activity to determine if we need to then do additional maintenance on those components. And so at every outage, we might take all of the sensors out of the system to evaluate their calibration status. And so if you want to take a sensor out of the system, then we have to isolate it from the system, remove it, apply a false load onto the sensor that will sweep across the range of the sensor, evaluate the calibration status, recalibrate if necessary, and then put it back into the system. And so if we're doing that every outage, run into a couple of problems, especially thinking about calibration assessment. EPRI did a study, the Electric Power Research Institute did a study of sensor calibration that showed that comparing the as found and as left condition of sensors in nuclear plants, maybe 5 to 7% of the sensors were out of calibration at an outage, right? So over an 18-month period. And then after doing all of the calibration activities, about 3 to 5% of the sensors are out of calibration. And they're usually a different set of sensors. So you have corrected sensors that were out of calibration, but you've introduced calibration errors into sensors that were just fine before. And so when we do this unnecessary inspection, then there's a chance that we're going to introduce a fault or introduce a problem into the equipment that wasn't there to begin with. And so we actually see that that the approach, the time-based periodic activities approach to inspection and maintenance could actually increase the risk profile of operating nuclear, just because we might be inserting some faults through imperfect maintenance activities. So we're looking at just updating the operations and maintenance paradigm in the nuclear industry for our current fleet of reactors. And when we think about the future fleet of reactors that might have non-light water coolants or different concepts of operations, we might do power peaking or load following or cogeneration, then we run into other problems that we don't have to worry about with our current fleet. A big one is that we don't have the operating experience with these new reactors. And so we don't have a rich history to rely on to tell us how frequently we should be doing inspection and maintenance. So we can look at the operational history of our light water reactors to estimate how often we need to inspect a reactor coolant pump. How often do we need to inspect our turbine control valves? And so we have something to guide us in setting those time-based schedules, even if they are still overly conservative. But when we look at advanced reactors, we don't really have any experience to rely on to help us set a schedule. Which I think will just push the schedule to be even more conservative while utilities try to develop that operating experience. We think about remote siting of micro reactors and some small modular reactors where we won't have personnel on site at the same rate that we do or at the same force that we do in our current fleet of reactors. We might have longer operating cycles, so some reactor designs that are intended to operate longer than 18 or 24 months between refueling outages. And so then if we wanted to maintain the same type of inspection intervals, we would have to go shut down the reactor, not to do refueling, but just to do maintenance that has to occur while the reactor's offline. So we have just all of these reasons that the current approach to operations and maintenance just isn't really working for us as well as we would like it to. It does a great job of keeping our reactors safe. We have great uptime and availability in our current fleet of reactors, but it is negatively contributing to the economic impact of operating a nuclear power plant. And so I think we see a lot of contributions from operations and maintenance costs toward the plants that are shutting down early. And I think that that we could see some issues when we try to license new reactors, if we try to license them using some of the same paradigms that we do with our current fleet of reactors. So when I talk about prognostics and health management, we're really thinking about how we can monitor equipment while it's operating to understand how it's operating. And so we might have our nuclear plant that is running baseload or in whatever operational status, and we're collecting data, just the normal process data, temperatures and flow rates and pressures and the neutron counts and whatever. And we also have inspection data. So we do send people around to do periodic vibration inspection of pumps and motors, for instance. And so we have a variety of data sources, not just the regularly sampled process data, but also other data that comes through the maintenance personnel. And so we can develop monitoring models, which is really where our data analytics and our machine learning comes in, where we can develop a model that will predict what we expect the plant to be doing. What do we expect all of our data to be? And so, so we really think of the monitoring model as an error correction routine. So we'll take the data that we're getting from the plant and look at, in the context of all of the data that we're collecting, what do we expect the data to be? What do we think the plant operation really is? And so then we can compare our expectation from the model to the data that we've measured to find our monitoring system residuals and evaluate those residuals to detect any anomalies or any kind of faults. So the residuals kind of naturally tell us how far from expectation we're operating. And so they'll indicate if there's any kind of degradation that's building up in the system. And then we can do diagnostics to try to understand what component is degrading and what is causing its degradation. So I might want to isolate to a specific component or a specific subsystem, and I want to identify the cause of the fault that is occurring. And then we can do prognostics where we predict how much longer could I continue to operate before I need to do something about it. So in the nuclear field, we don't think about running to failure, but just running until I am no longer confident that my component is going to provide the function that I need it to. So we kind of run to a reliability limit versus an actual failure of the component. And so we can then feed that remaining useful life information back into our operations and maintenance planning, our control system, anything like that. If we need to start planning for maintenance, then that would trigger hiring and ordering parts and all of these things that would let us plan our activities in a way that will be most cost efficient in the future without having to shut down the reactor unexpectedly to do maintenance. So just to, as a visual here, if we have these data are actually simulated data from a turbofan jet engine. But are very similar to the types of data that we see in a nuclear power plant, where if you just look at the raw data, it tends to look very stationary. So there's nothing that is obviously jumping out that would indicate that there's a problem. But we know that these data start at the beginning of life of the engine and they end at the failure of the engine. So somewhere between the first data point and the last data point, a fault initiates and grows to the point that the engine fails. And so we can't see it from our original data, but if we build up an online monitoring model and compare the predictions of the model to what we have observed in the data, then we can see in the residuals that there are some really clear indicators that things have started to change. And so what our online monitoring model really does is, instead of monitoring each individual variable, we're monitoring the relationships between the variables. And so we start to see when those relationships deviate, that indicates that that things are starting to change in the system. And so we can monitor the residuals of our online monitoring model and detect faults and start to diagnose the faults and do prognostics, where we might be able to take several of these residuals that show similar characteristics across a population of components experiencing the same degradation and combine those together into a prognostic parameter that is going to be consistent across a population, so that then when we start monitoring a new system and detect that there is a fault and start monitoring its prognostic parameter, then we can just extrapolate that out to our failure criterion, to where we're going to say that at this point we need to do maintenance, we need to do some repair, replacement, whatever. And considering the uncertainty in our data, the uncertainty in how our component will progress from faulted to failed, we can look at the uncertainty in our remaining useful life prediction and get kind of a probability of failure distribution over time. So this is really the crux of what we're trying to do to improve the way that we plan maintenance and inspection in nuclear power plants. And so I'm just going to talk probably really quickly. Sorry, I'm trying to keep an eye on time, but some of the ways that we're using this information to make decisions. So some of the work that we've done using prognostics and equipment condition information in decision making particularly for nuclear power plants. So the first thing that I wanted to talk about is what we call the enhanced risk monitor. So risk monitors really extend the idea of probabilistic risk assessment from like as built or as operated PRA model to a point in time. What's the risk of operating my system under the conditions that I'm going to operate it today, for instance. So, excuse me, our risk monitors can reflect the dynamically changing plant configuration. So if I take a component offline to do maintenance while the plant is operating, then I can go back to my PRA model and say that that component is unavailable. So it has, we can kind of consider that a probability of failure of 1 because it's not available to mitigate any hazards to the plant. And so so then we can feed that through the risk model and understand the increase in the risk of operating. How long can we be in this increased risks condition before we need to get the component back online, things like that. So so we have risk monitors in our plant now that look at the change in safety risks when we take things offline, when we change the way that we're operating. If the environmental conditions change, we can incorporate all of that information into a risk monitor. But the risk monitors that we use right now really rely on operating history for the probability of failure of the components that are going to stay online. So if I have, let's say, 2 trains, 2 coolant trains, and I want to take one train offline to do maintenance and I want to leave the other train online, then I could run my risk model, but it is just going to consider the kind of population-based probability of a train of a similar age failing over some period of time. And it's not going to consider the health of my actual train or the components in my train that are going to be online. So it may be that, maybe the pump has degraded a little bit, the valve is in a bad condition, and all of that's going to be lost to the risk monitor. And so the idea was trying to incorporate the real-time health of equipment into a risk monitor so that now our risk estimate when we change the plant configuration, for instance, taking things offline to do maintenance, that the risk monitor will reflect the condition of everything else that is in my actual plant operating in my actual conditions. And so we have this idea that we start with the initial PRA or the subset of our PRA model that goes into our risk monitor. And if we have some component that is operating like a pump, then we can monitor the condition of that component over time. And then say, I know that when my condition index gets to a certain level, or if it's not a perfectly crisp level, then maybe there's some uncertainty in my failure threshold. But when my component gets to that level, then I would consider it failed and I need to do maintenance on my component. And so then I can just perform prognostics to see when am I likely to cross that failure threshold. And if I look at any particular point in time, then I can see what the probability of failure at that point in time is, and update my PRA model or update my risk monitor using that information instead of using kind of the generic population probability of failure for this type of pump operating in whatever its condition is. So so to demonstrate this, we developed a prototypical advanced reactor, which just to demonstrate the concept. And so the first phase of this research, which was joint with researchers at Pacific Northwest National Lab, Pradeep Ramahali, who's at Oak Ridge National Lab now, but was a PNL at the time, and Garrel Coles primarily. We developed this completely made up prototypical advanced reactor design that is not based on any actual advanced reactor that anyone is developing for potential commercialization. But we just had two liquid metal reactors that were based on the EBR2 system. So two identical liquid metal reactors. Each was connected to a dedicated steam generator, and then those steam generators went to a common balance of plant. And so this was kind of our generic power block for the PAR model. And then, excuse me. And then from a risk perspective, we could look at this system, which is fairly simple, and decide what are the potential avenues from an initiating event to a core damage event, right? And so we can calculate the risk for a variety of initiating events that were postulated, just to demonstrate how we would incorporate an equipment condition into our PRA model or into our risk model. And so Garrel Coles really took the lead in developing these cut sets based on his experience in working in the nuclear industry. And so we had 30 cut sets that could lead to core damage, that were kind of feasible to lead to the core damage. We assumed that the reactor had a lifetime of 40 years. And then we looked at kind of varying the health of components over time. And so we would, for each component that contributed to the risk, then we would look at the decreasing health of that component or an increasing probability of failure. And then at some point we'd say, okay, this component has failed. We're going to do maintenance and bring it back to a like new condition and restart the degradation of that one component. And so, so you can see here in the bottom, this is our core damage frequency over time. And you can see where the drops are. We've done maintenance on a component that has reduced the risk. But in general, you can see that the risk varies quite a lot. And in this example application, we really started with the probability of failure that you would use using the current practice is around e to the -7. You know, we calculated, should add a dash line here, but so we calculated the baseline probability of, or the baseline core damage frequency around e to the -7 for our system. And you can see that in reality, when we consider the degradation of components that are operating in the system, we can change, you know, over an order of maybe 3 orders of magnitude from like beginning of life as we approach end of life of the reactor. And so this was kind of our first step of saying like, well, how much difference would it make? How much impact would we have if we considered the health of components in a risk monitor? And we thought based on these results, like that you would actually see a significant impact. So we maybe are making decisions based on the wrong data right now. And so if we could incorporate in a well-known probability of failure information or well-known health information for our components, then we could make better decisions. And we did look at you know, the impacts of uncertainty in the health of our components and how that impacted our overall core damage frequency, you know, with some error bars and everything. And I left those results out of here for time. But so that was our first look at using health information and prognostics to make better decisions. We also think about using information about how we're going to operate our components or operate our system to evaluate what if scenarios. So if I've got, you know, the same pump and I'm monitoring its health over time, and I say, I know that I'm going to be able to do maintenance at this point. Like I know when my next maintenance opportunity is, and I want to make sure that I'm going to get to that maintenance opportunity. Then, I might say, well, what would happen if I run my system under a high load and I have a high probability of failure before I get to my maintenance opportunity under that load? So then I can say, okay, maybe I reduce the load and that would reduce my probability of failure. And I can keep looking at, what the impact of the way that I'm operating my equipment is on the lifetime of the equipment to make sure that I'm going to get to my planned outage instead of having to shut down early to do maintenance. And so again, we're kind of taking into account the condition of our equipment to ensure that we're making the right decision about how to operate it and when we need to do maintenance on the equipment. And so then we looked at the same prototypical advanced reactor power module setup and developed a simulation model that was primarily developed by a master's student at UT, Xiaotong Liu, that models the primary system of the reactor, the steam generator, and the balance of plant, and also models the degradation of, in this case, we really only looked at the degradation of the reactor coolant pump and the intermediate pumps. So we just looked at 2 pumps, but you could also look at valves and heat exchangers and the steam generator and all kinds of other components. But as our initial step, we just started with these pumps. And we saw that as we degraded the pumps so that the pump was not able to produce as much flow as we were demanding from it, then it basically just had an impact on the maximum amount of power that could be output from the system. So we're really looking not at safety in this case, but at the economic viability. So, are we able to meet demand? And so you can see, as the primary flow rate, the capability of the primary pump decreases, then there's kind of a linear decrease between that and the maximum power output. And the intermediate pump has a little bit less of an impact, but it still shows a decrease. And so we looked at load following profile over 24 hours. This is very gross assumptions about what load would look like. But assuming that we have kind of a high load during the day and a low load at night, and then it goes back up. And so we used information that we were able to estimate about the health of the pumps based on the data that was being simulated from our model. So we kind of collected variables that we would expect to see in our model in an actual plant, collected those variables, developed a monitoring model and a prognostic parameter. And then we use that prognostic parameter to tell us the health of the equipment to feed into a control strategy. And so the control strategy that we ended up implementing was in the case of no degradation, if everything in all of our both sides of our power block was working well, then it would just equally distribute the power to say that if we want 90% power of our power capacity, then each reactor should give us 90% power. And if we want 50% power, each reactor should give us 50% of their available power. But then when we looked at implementing the control strategy when we had degradation in our pump, so just for one example of the primary pump degradation was equal to 0.2, we kind of fed that into the simulation model, generated the data, and did the prognostics, and fed those prognostics into our control strategy, which was really based on some fairly straightforward fuzzy logic rules. Then you can see that it's saying, if the primary pump in unit 1 is degraded, then we are going to ask unit 1 to make less power. And if unit 2 is healthy, so unit 2 is going to make up the difference. Excuse me. And so we were able to show that if we consider the health of the equipment, then we can excuse me. Sorry about that. So when we consider the, excuse me, the goodness. So when we consider the health of the equipment, we can balance the load across our two modules to meet our overall load demand. And then the last, excuse me, the last thing I wanted to talk about is kind of more recent. I'm sorry, I've got allergies, I think, but our more recent results to look at component health assessment to plan long-term inspection and maintenance needs. So in this case, we're looking at using the component health to plan outages. So if we are monitoring the health of the component, then we can say, you know, maybe this pump, the health is degrading, and there's very clearly going to be in a bad condition at our next outage, and so we're going to do maintenance on this one. If we're monitoring this valve, then we'd say this valve is not degrading as quickly. It looks like it's going to make it not just to this outage, but it will make it to the next outage, to our subsequent outage. So if I am confident enough that I will get to the subsequent outage, then there's no reason to do maintenance at this outage. So I can defer the maintenance of that component. And then if I have another component that is likely to make it past this outage, but not make it to the next outage, then I need to do maintenance. You know, so I can kind of look at the remaining useful life and the distribution of the remaining useful life to decide when I needed to plan maintenance and inspection for each component. And if I am very confident that I will get to at least the next outage, then I'll just defer the inspection. I won't do anything with that component. And so in a previous project, we were looking at developing a maintenance planning optimization routine, and develop this routine not considering prognostics, but just considering the cost of doing maintenance and the risk associated with maintenance. And so this optimization routine was really developed with online maintenance in mind, to say, you know, I want to figure out the cheapest way to do a set of maintenance tasks that need to happen, say this week. I've got task 1 through 12 that I need to do this week. What's the best way to get them done? And then we could consider risk implications to see, if I take all of these things offline at the same time, how does that impact the risk? And so kind of going back to the risk monitor idea to say, is this going to be acceptable? And if it is not acceptable, then we'll go back and add another constraint to the optimization problem and re-optimize and get a new solution. So using this tool that was developed for maintenance planning optimization to minimize the cost of the maintenance schedule, subject to the qualifications of crews that we had available. So we needed people who were able to do the work that needed to be done. So, you know, we couldn't maybe schedule the same electrician to do 2 things at the same time. We also could consider how long it would take to do each one of the activities, and if there are precedence relationships. So, maybe I need to do like activity A on my pump before I do activity B. So the optimization can make sure that the maintenance is performed in a meaningful order, in a meaningful way, and then consider the risk in terms of all of that. So we have this maintenance planning optimization routine that, like I said, was developed in another project, and we've taken that and applied it to this outage planning idea. And so this is work that is very much still ongoing. This is just our preliminary results, but we started just with the primary containment isolation valves for a BWRX 300 like design, where we had identified, I think, 18 different valves, 18 or so different valves that would need to be maintained at some point, and developed a periodicity of how often we would do each activity. So, if it needed to be maintained every single outage, every other outage, every third outage. And so we have this kind of generic outage schedule that is following the current approach of doing maintenance and inspection on a time-based schedule. And so you can see, like, well, we always inspect and monitor these systems in outage 1, and then these systems in outage 2, and then these systems in outage 3. You can see, like, some things are at least once every 3 outages. I think we have 4 main steam valves, so the 4th one would be an outage 4. And some things happen more frequently. Some things happen every single outage. Some things happen every other outage. And so when we apply the this optimization routine to figure out the best way to schedule all of these activities, and just considering labor costs, then we can see, okay, if we don't consider prognostics, so we know that we have to do these activities, we just want to know the fastest way to get them done. Then we're looking at costs at each outage of $92,000 to $95,000 just for these activities, which again is ignoring a lot of the cost of outage maintenance. But then when we considered prognostics, so for every system, we looked at a notional health indicator of that system and how it would evolve over time. And so then we could see here on the lower left, we have kind of our basic outage schedule. All of the items that are highlighted in blue occurred as planned in the outage. The component was at a health condition that it was necessary to go ahead and do maintenance and not try to wait till the next outage. Everything that is in green, we were able to defer to a future outage. And then things that are in orange were kind of pulled forward. So they had that maintenance occurred sooner than was expected or was initially planned. And so making all of these switches, and we actually ended up with these 3 outages in the lower right table, or kind of lower middle table of what actually needed to be maintained during each of our 3 outages. And then applied the same, once we have identified these are the subsystems or the components that need to be maintained, then we can apply the same scheduling routine to try to figure out the cheapest way to do it. And so we end up again with about a $92,000 outage, but then the second outage, which has more components being maintained, but they have the activities that we have to do associated with those components are less onerous. So we ended up with I think total cost of without considering prognostics, we're looking about $280,000, and with considering prognostics, we're looking about $240,000. So we saved about $40,000 in this like notional case with just one type of components, just looking at these valves. And so this is work that is very much still ongoing with GE Research and GE Hitachi and Oak Ridge National Lab. Things that we haven't considered so far in this work is the risk. So as we defer maintenance, does that increase the risk of operating, from one outage to the next, if I've deferred maintenance over that period, then how does that affect the risk of operating? We need to look more at kind of exploring the stochastic nature of the prognostics, because we've looked at an example case, but we're running through multiple examples to see kind of on average how the prognostics helps the cost of outages. And then we're also incorporating some more systems in. So this is very much ongoing work, but is another, I think, really useful way to think about using prognostics. Not necessarily to say I know exactly when my component's going to fail, but just to say, am I confident that it will make it to my next maintenance opportunity? And if so, then I'm going to defer it and I will reevaluate it when I get to my next maintenance opportunity. And if I'm not confident, then I will go ahead and do maintenance on it now. So, so prognostics as a information source about the health of the components that we're operating can really inform our controls algorithms, our operations and maintenance planning, and really our decision making in the nuclear fleet. We kind of see the whole suite of PHM, so from data collection through monitoring and detection and diagnostics and prognostics as a way to augment the lack of historical operating experience in our next fleet of reactors. And so we get more information about what is happening right now, which can kind of make up for the fact that we don't have as much operational experience. We don't have a nice history of information to rely on, so that we don't have to be overly conservative in how we operate. And so, the current condition assessment really doesn't go far enough. I think there are a lot of research opportunities that still exist to try to develop this and get it ready for deployment in a nuclear facility. So we've got non-destructive measurement methods to look at especially passive components, but even methods to measure the health of active components. There's a lot of work to do in algorithms and prognostics. So how we're actually going to monitor our systems and predict forward how the health is going to evolve, and then trying to integrate that into results in a way that is acceptable to the utility, to the operators, and also to the regulator. And so with that, I will stop. I think I've gone a little bit longer than I meant to, so be happy to try to answer any questions.
Thank you, Jamie. We've got a couple of questions in the chat if you'd like to take a look at those.
Let's see.
From Ryan and Matt.
Okay, so the question, so the majority of the operating fleet has moved to a risk-based or risk-informed decision-making approach using PRA and existing plant data. So what is the timeline or the turnaround time expected of updating your risk monitors and plant models when you discover an issue? And so with the risk monitor, if I'm understanding the question, I think you're asking like how fast can you reevaluate the risk model? And so like for a full scope PRA, that's typically like an onerous problem. But when we look at the risk monitor, it's a smaller subset of the PRA model that can be evaluated much more quickly. And so I think that that's one thing that we were looking at. How do we make sure that we're not increasing the computational complexity of risk monitors to the point that they wouldn't be valuable for day-to-day decision making? So it's not going to give you like second by second decisions, but if I want to make a plan for tomorrow, I need to be able to evaluate my risk monitor in minutes, not in hours or days. And so I think that if that hopefully that kind of addresses what you're asking about.
I think so. Thanks, Jamie. Yeah, so I remember we would always do, annual updates to our PRA model at the plants, and that would incorporate, any plant modifications. I'm just wondering, so if those risk monitors are updated on a much more frequent basis, does that get logged into kind of, hey, when we do our annual update, we'll update our PRA model, or just wondering if you knew more about like the turnaround time for the PRA piece as well.
Yeah, so I think yes, my understanding, and I've never been a plant employee, so this is maybe a little bit of an academic understanding. My understanding is that when you do those like updates or outage updates, that you're updating like changes to the facility. So if you change a subsystem or change the pump or make a design update, then those would get incorporated into the risk monitor, or into the PRA model. But the kind of updates to the risk monitor that we're looking at are more changing the probability of failure, right? So I want to update the probability of failure, the probability of initiating events, whatever, based on the monitoring that I'm doing in my plant. And so that would be something that would just be continuously updated in terms of like as components continue to degrade, or you do maintenance and components come to a healthier condition, then you would update just the probability of failure part of the model, not the fault trees or the event trees or anything. And I see Matt's got a hand up, which he might have some input.
Oh, very cool. That totally makes sense.
Yeah, right. I think so mine was more of a comment less than a question. I do have some questions because it's very interesting. Again, it goes to, how we plan maintenance, how we plan outages online also. A lot of it in the operating fleet is built on experience. We know how we've maintained these systems in the past. And so the value in this in not having that operating experience, and Jamie, I'm really glad that you kind of highlighted that, because that's where I see kind of most of the benefit. And then as a plant employee, former plant employee, anytime any piece of equipment that had an input into the PRA model, including external events, as I mentioned there, SROs, the licensee, the actual licensed operators are, updating the PRA real time. In a manual fashion. I mean, we do run cut sets again each time based on what is already built in, like in terms of maintenance that's ongoing at the facility, any equipment that is out. And so, Jamie, I guess what coming from the operating fleet perspective, really what you're trying to do with this risk monitor is automate this process. So I don't have to. As an operator, I can see how the model updates in real time. I don't have to be the one kind of manually selecting the component and then running the PRA model again, or the cut sets again, just to see where my core damage frequency comes out. And again, I think these principles are already widely used now in the fleet. We have risk-informed tech spec completion times, which is really based on the PRA. It tells us, how we set our times where we have to take an action under tech specs. So I guess I'm curious, Jamie, just to ask and clarify, one, if this risk monitoring system is being used to make safety related decisions, I mean, inherently that has to go through a QA process. And I'm interested to see how this factors or integrates with the current paradigm with the regulator and how this, would be incorporated as kind of more when you get into safety related components, how this system can be qualified in that sense. So thank you for the presentation also.
Yeah, and that's a great point, and is beyond. So I guess as a university researcher, we don't get in as much, we stay at kind of low TRL level research. But I think that because of the NRC's move toward accepting risk-informed operations and risk-informed changes, and kind of moving a lot of the inspection frequencies out of licensing basis and into an operator controlled space. I think that the framework is there, and the groundwork has been laid for them to accept this idea. But I agree. I think there would be a lot of QA that would need to be done because like you said, a big part of the value is the automation of having a monitoring system that will just feed into your risk monitor. And so you don't need to manually go in and change everything. We would, in an ideal world, things would be connected at the plant so that the data from the process, the data from your computerized maintenance management system, all of that information could be distilled and evaluated to get the health and the prognostics information, and then that would just automatically flow into your risk monitor and into any other systems that you're using for operations and maintenance planning. And so I think that there's, from the utilities that I've worked with, that communication is not there right now. The communication channels between process data and CMMS data is not straightforward.
Yeah, it's a manual process. It takes somebody to move the data, like, you know, from one place to another to get this to go. But if it is automated, again, I think the human factor is benefits here. Just in the control room, if I'm having to spend time looking at the PRA model to evaluate, obviously I need to make decisions on that, but it's also taking an operator's attention away from something else, right? So there's a lot of touch points here that I can see and how this provides benefits. I think it's very interesting. And yeah, I understand, you know, being at the academic level, but, you know, regulators got to make decisions on some of these things based on you know, the fundamentals of how these systems operate. So again, I just want to say thank you very much for the presentation. It's really interesting stuff. And yeah, I see a lot of application and to fill the gaps on OpEx with advanced reactors. And that's a, you know, very important, very crucial thing as we see these systems deployed.
Great, thank you. And I'll be happy to maybe send the PowerPoints to Joe or to somebody if anybody wants them.
Yep, we'd be able to post them on our website. I don't see any other questions. Appreciate you pushing through your allergies. We're just starting on our allergy season up here. We just barely got rid of our snow. But with that, I thank everyone for participating, and we'll get the video posted on the Idaho ANS website as soon as we can.
Great, thank you again for the opportunity.
Thank you, and have a good day.
Thanks.